In this section, 14.1, we'll be looking at several sections in 14 having to do with mechanical waves and sound. First of all, we need to look at a definition of certain key concepts associated with waves. First of all, what is a wave? Well, a wave is a traveling disturbance in a media that carries energy but not mass. So energy is moved from one place to another, but mass is not. Let me give you an example. If we are fishing and we look at a wave that's coming along on the water, and here's a float, or a fishing float, if you stop and think of what happens with that float, even though the wave is moving in this direction, the float moves up and down as the wave passes, and so does the boat. Therefore, the wave is transferring energy because the float wasn't moving. Now it oscillates up and down, and so does the boat. So energy has been brought to this point, but the mass is not being moved. Otherwise, we'd see the float and the boat move along with the wave, and that does not happen. So the critical thing is it carries energy, but does not carry mass. Fourier's theorem, Fourier was a very famous mathematician and physicist, F-O-U-R-I-E-R. Fourier's theorem is incredibly important in physics. It says that all wave disturbances are linear combinations of sines and cosines. That means no matter what this disturbance is like, if it's periodic and repeats itself again and again, then we can find different types of sines and cosines of different amplitudes that will add up and give us exactly that wave. In particular, we'll find out that any water wave or any sound wave or any light wave can be made up of sine and cosine waves. It turns out that even if the wave is not periodic, if it never repeats, then no matter what this function is, as long as it's single valued, even though it doesn't look like a wave, it could look like this, have a lot of irregularities to it. It can still be made up of sines and cosines of different frequencies. And this is what Fourier's theorem tells us. Let's look at our core concepts concerning waves. First of all, what does a wave look like? Well, y, as a function of x and t, is going to describe how large the wave is. Here's a wave going along, travels this way. This is going to be x, and over time that wave moves, and so later on it will look like this. So it's moving from one place to another. So it depends both upon position, there it is plotted by position, and it depends upon time. That is the amplitude. This is the amplitude of the wave. How can we write it? Well, the simplest wave is an amplitude times the cosine of omega t, that's the time dependence, minus k times x, plus phase delta. Well, I've got it kind of messed up there, but here it is typed out carefully. Why don't I rewrite that? A cosine of omega t, that's angular velocity times time, minus k times x, this is called the wave number, times x, plus a phase. And that'll describe what this wave is like. And this is, of course, a sinusoidal wave. And we can say at position equal to 0, time is equal to 0, this will give us the phase of that wave, whether it starts out at the maximum, which would be a cosine, the phase would be 0. If it started at minus 1, then the phase would be pi. So different phases allow us to position the wave at time t is equal to 0 and x equal to 0 at different positions. Well, let's look at each one of these terms and see what they are. First of all, we can talk about the period of the wave. T is the period, and the period of the wave is the time required for one cycle. How long does it take one complete cycle of this wave to oscillate. The frequency is the number of cycles per second. And it's measured in hertz. A hertz is 1 hertz is 1 cycle per second. In other words, 1 complete oscillation or 1 complete revolution. The amplitude of the wave is this term here that multiplies the cosine, because the cosine has a maximum of 1 and then minus 1, and so the amplitude factor can make this larger or smaller as a wave, and so this just determines the amplitude. The wavelength, lambda, is the distance between 2 equal points in the wave. So the distance from this crest to this crest, or this trough to the next trough, would be lambda. Lambda is going to be equal to the distance between equal points on the wave. Finally, the phase we've discussed, and it is the position of the wave, whether it's here would be 0, here would be pi or 180 degrees. The angular velocity, we're now going to go over the angular velocity and the wave number. So let me move the paper up and say omega is equal to the angular velocity. And k is equal to what is called the wave number. Well, what is this angular velocity? How can we understand that? Well, the cosine, if everything else is fixed, the cosine will oscillate in one period through an amount of 2 pi, which means that omega times t, the full period, that amount of time, will equal to 2 pi. Consequently, omega is 2 pi divided by the period. So this is an incredibly important equation. It tells us how to understand the angular velocity. It is 2 pi divided by the period. Why? Let me repeat. If we look at the cosine of omega t, when omega times the full period, capital T, goes through, in other words, the wave goes through one full oscillation of 2 pi, that's 1 cycle, then omega times that must equal to 2 pi. And therefore we can calculate that t is equal to 2 pi over omega, or omega is 2 pi over t. The next one is exactly the same. K times x. Well, when x goes through one wavelength, k times x must go through 2 pi. So k times a wavelength, this is the time for 1 cycle, this is the distance for 1 cycle, must also equal to 1, must equal to 2 pi. Therefore, this tells us how we understand k. K is equal to 2 pi divided by the wavelength. The wavelength and the period are things that are intuitive. K and omega, the wave number and the angular frequency, are not. What are the other 2 core variables that we have here? Well, if we know the period, then we also know the frequency, because we have this very important formula that the period, that the frequency is equal to 1 over the period. If something oscillates in 1/4 of a second, in one full oscillation, it's going to oscillate 4 times a second, or 4 hertz. Therefore, this equation, which always applies, allows us to take this and say, well, omega is also equal to 2 pi times the frequency, because I've just taken this 1 over t and replaced it by the frequency. Now, what else do we know? Well, we know something else very important. The other core equation here is that the wavelength times the frequency is the velocity of the wave. These two equations here apply to all wave phenomena. And once we know this, then if we have the wavelength, we can compute the frequency or vice versa. The critical thing is, what is the velocity of the wave? How fast is this wave moving? Well, the two things that we're going to be concerned with mainly in this course are the speed of sound and the speed of light. The speed of light, the velocity of light, is c, which is 186,000 miles a second, or right at 3 times 10 to the 8th meters per second. You can use either one of those. These you have to memorize. The other is the speed of sound, the velocity of sound. And the speed of sound is about 1,100 feet per second. Or, more precisely, 331 meters per second. And we'll talk about this in just a minute. So what are our core concepts here? Number one, what is the form of the wave? Y is a cosine of omega t minus kx plus delta. If you see that in numerical form, be able to know what you call each one of those things. The period t is the time it takes for one full cycle. The frequency f is the number of cycles in each second, measured in hertz, or cycles per second. Period, of course, is measured in seconds. Amplitude is how high the wave is. It multiplies the cosine. The wavelength is the distance between two equal points on the wave. Omega is the angular velocity. K is the wave number. And those two things can be interpreted by looking at these formulas. Omega times one full period is 2 pi. K times one full distance in the wave is 2 pi also. Then using these equations here, we can extend these equations and get much more interesting information.